IcyTower is a very simple but fun game. We play Harold the homeboy who tries to get up this tower as far up as possible. Our goal is to achieve a score as high as possible. A good way to achieve that is to increase our jumping height by gaining horizontal momentum, as this will give us bonus combo points. Of course, over time the game gets more tricky with fewer, shorter and faster moving platforms. And that's already pretty much the game. Oh, that's right, you're currently watching not a human playing but an AI that I trained. But how did we even get here? Let's start at the very beginning. This is Nick. He's my good friend, roommate and coding partner, but most of all he is what we call here a nerd. Recently we had our usual discussion about who's the bigger nerd, and of course we settled this with a game of IcyTower. Whoever wins clearly has to be the bigger nerd. Unfortunately for me, he kicked my ass. So I did what any person would do in my situation and tried to build a superhuman AI. This is what happened. Hi everyone and welcome to the video. What you see here is the finished code for the AI, but I want to give you a basic idea of how this code works before we actually execute it. So let's start over with a blank slide again, and I will quickly guide you through the most important features, most important functions of this program. Now please realize this is not meant to be a tutorial, so I won't go into too much detail when it comes to the exact syntax or code. I just want to give you a basic idea of how the main functions in this program work together and how each of these relatively simple puzzle pieces put together form a relatively complex program. So let's begin. So the way any machine learning model works is with data, right? So we need to extract some sort of data so we can train our model, and then when it's trained based on these data, it can also make informed decisions. So the big problem here is how do we extract the data? Because I didn't write this program, I don't have access to the source code or any information running in the background while I'm playing. So I need to figure out a new way to extract all the information I need. And the way I went here is by taking rapid screenshots from my screen, and then hopefully later I will be able to detect everything I need in those screenshots. But that's a problem for later. For now, let's concentrate on taking the screenshots correctly. Fortunately for us, there are already existing packages in Python which we can just use to take the screenshots for us. And the package I went here with is called MSS. So the first thing we actually need to do is create a MSS instance. This is going to be eventually the thing that does take the screenshots for us. And next we create a function called take screenshots. And in this function, we just tell the MSS instance where it is supposed to take the screenshots. Because if we look at the game, of course, we will realize we don't need screenshots of our entire screen, but it's totally sufficient to take screenshots of this area of action here. So all I did was look up which pixels those are and hard code them in here. And then finally, we store those screenshots in a variable. And finally, for some computational reasons, which to be honest, I don't understand, but according to my research, that's what we gotta do, is we need to convert the color of the screenshot. What that looks like we are about to see in a second. So what we do now is just execute the function really quick in an endless loop and see what it actually looks like. So yeah, seems about right. If we move, it detects that. If we are in the left corner, we are still in the picture. If we move to the right corner, we are still in the picture. And at the same time, we don't cover any unnecessary space. So it seems about right, which means we can move on to the next step. So you could argue that our program does have eyes to see now, but it doesn't have yet brains to understand what it sees. So it can't extract information from the pictures it takes. And that will be our next task. The logical next question is, what kind of information do we even want our program to extract from those screenshots? A good way to think about this is just imagine yourself playing the game. If you play the game, what kind of information is your brain supposed to extract from the things your eyes see? And a very obvious one here is the location of our avatar, right? You need to know where you are in the map here in order to know where to go and therefore which actions to take. And my way here is to detect a certain pixel color, because here these skin colored face pixels, they are pretty unique in the game. So if we are able to extract the locations of those, then we will be able to know where the face of our agent is and therefore the location of our agent. First, we need to tell our program what kind of color it is supposed to detect. And here we just need to understand that for a computer, a color is nothing but a number, or in color pictures, actually 3 numbers for the amount of red, green, and blue. So what I did here is just look up manually what the face color of our agent means in terms of numbers to our computer, and then just write it down here. So whenever a pixel is within this range here, between those colors, then it is supposed to get detected. And for that, we need to write another function. So we call that function getAgentCoordinates. And the first thing we do here is create a mask. So what a mask does is it filters out all the pixels that are not in our desired range. So whenever a pixel is not within this range of colors here, it gets filtered out. So that means the remaining pixels here, we store them in another variable. And those are the ones we want to find the location of. So what we do is we simply calculate the mean in X and Y direction for each of our detected pixels. And then this should hopefully be the location of our agent. So hopefully this works. We will check this now. The way we do this is we tell our program to actually calculate the X and Y value. And then so we can check where it thinks our agent is, we tell it to draw a circle around that area. So if we execute this program now, then we can see now there's a red circle around our agent. And if we move, the circle moves with us. Very good. If we jump, the circle moves with us. So looks pretty good. So which means we can move on to the next step. Once we're able to detect the coordinates of our agent, it will also be quite simple to calculate the speed of our agent and the movement direction. For that, we just need to create a queue which stores not only the current location of our agent, but also the location from the previous screenshots. And if we just simply subtract these two values from each other, then we will be able to know how far the agent traveled within the past 2 screenshots, and therefore know then the average speed he had in that time. So we create a function here which we call getAgentSpeed, and we pass it 2 arguments, the current X and current Y coordinate of our agent. And the first thing we do is we update this queue here. And then we do exactly what I just said, subtract the 2 values in the queue from each other, so we get the velocity in both directions. Remember, this doesn't only tell us the speed, but also the movement direction, because if the velocity in X direction, for example, is positive, we know our agent is traveling towards the right. If it's negative, he's traveling towards the left. And of course, this also works in a vertical direction. Now that we can detect our agent's location, velocity, and movement direction, there's actually only one more thing left for us to detect from the screenshots, and that's going to be the platforms, right? We need to know where those platforms are, so we need to know where to jump, of course. And the way we go here is also similar to the way of detecting our agent's location. We create a color range which we want to detect. In this case, that's here this upper end of our platforms. I hope you can see this. And I again just manually looked up what this color means in terms of numbers. And then we create a dictionary which will later store the coordinates of our platforms. And then we can already start to define another function here, which we will call getPlatforms. And the first thing we do here, again, similar to our agent detection, is we create a mask. What this mask here does is it makes all pixels black except the ones in this color range. So if you would output this image, it would be a completely black image, and only here, these areas here would be white. And then we use a function which basically detects shapes of lines. So if many pixels are rowed up in a row, then it detects that this is a line. The problem here is this function is very accurate. So it actually doesn't detect a platform like this as one line, but it detects it as, I don't know, 5 or 10 lines very, very close to each other. So we don't want to have in the end like a output that tells us it sees 100 platforms here and some of them are just stacked very close. But we really want our program in the end to see 1, 2, 3, 4, 5, 6 platforms in this image. So what we need is one more thing in this function, and that's like a merging algorithm which just merges those very, very close lines to one thick line. So this should already work. Of course, now we want to check again if it really does work. So we will, again, similar like the detection of our agent, we will tell the program to draw a line where it thinks a platform is. So if we run this program now, yeah, so we see we still have the red circle around our agent where the program thinks our agent is. And now we also have white lines where the program thinks our platforms are. And if we jump, yeah. So the platforms move a little bit up and down, but that shouldn't be a big problem. But yes, it seems to pretty reliably detect the location of the platforms. Our next step is actually the simplest one. It's only a few clicks. First, we click that like button under this video, then we click the subscribe button and maybe even the bell. Okay, that means we have all the details now we need, or almost all. And while I will add some more bug fixes and do some fine-tuning on the code, you can watch my explanation of the machine learning algorithm, which we will use in a second. So enjoy. The overall term for the kind of machine learning we are about to use is reinforcement learning. In a nutshell, reinforcement learning kind of works like this. Initially, our program behaves in a super random way, and if just by chance it does something right, such as climbing up a platform, we reward it with positive numbers. If it does something wrong, such as dying, we punish it with negative numbers. Over time, our program will learn which behavior leads to positive reward and which behavior leads to punishment and act accordingly. The exact reinforcement learning algorithm which we are about to use is called neuroevolution. Any machine learning model works with inputs which get passed to a black box, and the black box works with those values and ultimately returns output values to us. In our example, those input values are the game situation, the coordinates of the platforms, the agent, and so on. And the output values are what our program thinks the best action in this moment is. You can imagine this black box in between input and output as some sort of brain which takes the input data and then draws conclusion which actions are currently best in the game. Only that in the beginning this is much less of a human brain and much more of something very, very simple like an ant. Now, the way the neuroevolution algorithm works is it takes not only one of those very simple neural nets, but it actually takes many of them. Just by chance, each of those neural nets, or ant brains, if you will, has a different behavior, and therefore there will be smarter ones and less smart ones, and it will be only those smart ant brains which get the right to procreate, and by that create the next generation of ants. Amongst this generation, which will be on average smarter, there will be again the best performing ants, which will then create the next generation of ants. Until finally the ants don't have too much in common anymore with ants, and they evolved much more to maybe, let's say, something like a sheep or something much more intelligent. And if we keep training there, and we are lucky, the sheep maybe evolved to something which is almost as smart as a human. And if we keep training and we write a great program, maybe we even get to a superhuman level. So I hope you got a basic idea now of what is about to happen. If not, don't worry. I'm sure most open questions will be answered throughout just watching the training process now. And of course, I will give more explanations then. Before we can start the training process, there's only one last thing to talk about, and that's the probably most complicated part of the entire program. and that's the reward system. So it just told you that reinforcement learning always works with some kind of reward system where we reward good behavior, if you will. In IcyTower, this reward system is just gonna be this score down here. So we somehow need to tell the program which score it achieved, and then it can compare the performance of each neural net and then let evolution do its thing. Now the problem here is, of course, how do we extract that number? And here I trained a neural network that is able to read those numbers down here. So I pass only this part of our screenshot to the neural net. It detects the shape of the pixels in there and then is able to read these numbers down here. So let me just prove to you that this feature actually works. Now watch the output in this window here. Initially it detects that we have 0 score, and as we gain score, 70, 80, set back to 60, 100, 110, 140, it detects that as well. Of course, I tested that all a bit more extensively, and it seems to work really, really well. That means we can start now with the training process. So we just start the game, execute our program, and enjoy the show.
you